Let's say for a second, you are driving your car in the middle of nowhere, and for some reason, you lose the route to your destination. You might panic for a second, but then you remember, you have GPS, don't you? That little blue dot on your map knows exactly where you are heading to because satellites in space are watching you. We tend to think of GPS as this universal God mode grid that covers everything. If it works in the middle of the Pacific Ocean and it works in the Sahara Desert, surely it works in space, right? After all, the satellites are in space. But here is the terrifying reality. If you took your phone, hopped on a rocket, and flew past the International Space Station, your Google Maps would eventually stop working. The blue dot would freeze. And if you kept going toward the moon, you would be flying blind. Because here is the secret that NASA doesn't usually talk about. The global positioning system wasn't built for space explorers. It was built for nuclear submarines and tanks down here on Earth. So how do spacecraft know where they are? How does a probe, millions or even billions of kilometers away, know how to navigate with extreme precision? The answer isn't mystical, it's engineering. Because spacecraft don't rely on GPS. They rely on physics. And today, we're breaking down exactly how the navigation system actually works once you leave our beautiful Earth behind. Let's roll. To understand why GPS fails in deep space, we first have to look at what GPS actually is. It's not a magical force field, it's a clock. A very, very precise clock. There are about 31 GPS satellites whizzing around the Earth right now. They orbit at an altitude of roughly 20,200 kilometers, about 12,500 miles. Each one of them is constantly screaming out the time and its exact location. Your phone listens to 3 or 4 of them, compares the time delay, and uses trilateration to pinpoint you. Now, here is the first part of the puzzle. The International Space Station orbits at only 400 kilometers up. That means the ISS is underneath the GPS satellites. It's looking up at them, just like we are. So yes, the ISS actually uses GPS. In fact, it uses it to calculate its speed and orbital position with insane accuracy. But what happens if you go higher? There is a specific zone called the terrestrial service volume. This is where the signal is strong. But once you fly past that 20,000 kilometer altitude, you are technically above the GPS constellation. You might think, so what? Just turn around and listen to the signal coming from behind you. But it doesn't work like that. This is the flashlight problem. GPS antennas are directional. They don't broadcast into the void of space. That would be a waste of energy. They point their antennas directly at the Earth's surface. They are shouting down, not up. So, if you are a weather satellite in geostationary orbit 36,000 kilometers up, you are looking down at the back of the GPS satellites. You are in the quiet zone. You are effectively invisible. Or are you? Engineers hate waste. But sometimes waste is exactly what saves you. When a GPS satellite blasts its signal toward Earth, it's mostly a focused beam, but radio physics is messy. You get these things called side lobes. Think of it like a flashlight in a dark room. You have the bright spot in the center, but you also have that faint, spillover light that hits the walls on the side. For decades, GPS engineers considered these side lobes to be just wasted energy. Spillover signal that missed the Earth and drifted out into space. But then NASA had a crazy idea. Meet the MMS mission, the Magnetospheric Multiscale Mission. These 4 spacecraft hold the Guinness World Record for the highest altitude use of GPS. They fly in a highly elliptical orbit that takes them nearly halfway to the moon, about 150,000 kilometers out. That is way above the GPS satellites. They are deep in the dark zone where the main GPS beams don't reach. So, how do they navigate? They listen for the whispers. They carry incredibly sensitive receivers designed to catch those side lobe signals, the spillover radio waves that miss the Earth and are leaking out into the void. Imagine trying to hear a conversation happening in a soundproof room, just by listening to the vibrations on the glass from across the street. That is what MMS is doing. By tracking these faint, accidental signals from GPS satellites on the other side of the Earth, MMS can figure out its position to within 10 meters, at a distance of 150,000 kilometers. That is like shooting an arrow from New York to London and hitting the bullseye. But there is a limit. Side lobes can only get you so far. Once you go past the moon, the GPS signal is gone. It's too faint. The whispers stop. If you are the Voyager probe or the Mars Perseverance rover, there is no blue dot. So, how do we not lose billion-dollar robots in the infinite blackness? We have to do it the old-fashioned way. We have to ping them. This is the Deep Space Network, or DSN. 3 massive radio telescope arrays placed 120 degrees apart around the Earth, one in California, one in Spain, one in Australia. This ensures that no matter how the Earth turns, one giant ear is always listening to deep space. Here is how navigation works out there. Earth shouts a radio signal at the spacecraft, Marco. The spacecraft receives it, processes it, and shouts back, Polo. We measure the time it took for that signal to make the round trip. Since we know the speed of light is constant, roughly 300,000 kilometers per second, we can calculate the distance exactly. To get the speed of the spacecraft, we use the Doppler shift. Just like an ambulance siren sounds higher pitched when it comes toward you and lower when it goes away, the radio frequency from the spacecraft shifts slightly depending on how fast it's moving. But there is a massive problem with this system. It's not real time. If you are on Mars, that signal takes roughly 14 minutes to get to Earth and 14 minutes to get back. You are navigating with a half-hour lag. And worse, it relies entirely on Earth. If the Deep Space Network goes down, or if the Earth were to disappear, the spacecraft would be lost forever. It has no idea where it is. It's just a dumb piece of metal waiting for instructions. We need a way for spaceships to be autonomous. We need a GPS that works across the entire galaxy. And nature has actually built one for us. In 1967, astronomers discovered something terrifyingly precise in the sky. Dead stars. When a massive star dies, it collapses into a neutron star. Some of these spin incredibly fast, hundreds of times per second, and as they spin, they blast out beams of X-rays. From Earth, they look like flickering strobes. We call them pulsars. And the timing of these pulses? It's rivaled only by atomic clocks. They are the most stable natural timers in the universe. This leads us to the holy grail of space travel, XNAV, X-ray pulsar-based navigation. Here is the concept. Instead of locking onto GPS satellites, a starship locks onto specific pulsars. It sees pulsar A flashing at 100 beats per second. It sees pulsar B flashing at 75 beats per second. It sees pulsar C flashing at 300 beats per second. By comparing the arrival times of these X-ray pulses, the ship can triangulate its position anywhere in the solar system or even the galaxy without ever talking to Earth. This isn't just sci-fi. We've already tested it. In 2018, NASA used an instrument on board the ISS, which goes by the name Station Explorer for X-ray Timing and Navigation Technology. It stared at 4 pulsars, measured their beats, and successfully calculated the location of the space station to within a few miles, completely independently of GPS. This is the future. When humans eventually travel to Mars, or the moons of Jupiter, we won't be looking back at Earth for directions. We'll be looking at the stars. So, does GPS work in space? If you are close to home, like the ISS, yes. If you are halfway to the moon, only if you are smart enough to listen to the echoes. But if you are going to the stars, GPS is useless noise. The further we go, the more we have to relearn how to navigate. We started by looking at the stars with wooden sextants on sailing ships. Then we built artificial stars, satellites, to guide our cars. And now, as we prepare to leave our home planet behind, we are circling back to the beginning. We are building metal sextants to once again guide our ships by the light of the stars. Thanks for watching. And if you want to know how we actually keep the air breathable on those ships without carrying a million tanks of oxygen, check out this video right here.